Hello, good morning. Uh, Today I am going to discuss about the convergence of series. At first, I am going to discuss about the convergence of any series using alternating series test. Alternating series is related to the word alternate, where alternate means change the direction or change the sign of consecutive numbers frequently, one by one. Now let an is a series where an is greater than 0, then the alternating series this and this will converge if the following two conditions are satisfied. That means limiting value of an where n tends to infinity is equals to 0 and a n plus 1 is less than a subscript n for all n. That means the series will be gradually decreasing. For example, check the convergence of the following series where summation n tends n equals to 1 up to infinity and minus 1 to the power n by n square. Now if I compare this series with any one from the definition, we can write that n equals to 1 by n square. Now we are going to determine the limiting value of an. That means if I substitute the value of an here, I can see that 1 by infinity square, that means 1 by infinity, so this is 0. Now we should check whether the series is decreasing or not. Say that if I write a subscript n plus 1, which should be equals to 1 by n plus 1 whole square, that means a that is less than n square. This would be clear from this example. Suppose n equals to 1. If n equals to 1, then from the left side I will get 1 by 4. Okay, if I substitute n equals to 1, I will get a2 equals to 1 by 4, and in the right side it would be only 1. So 1 by 4 is clearly less than 1. So we can decide that this is decreasing gradually. So the two conditions from the definition are satisfied by this series. So we can easily conclude that the series is convergent. Okay. From the second example, now see that check the convergence of the following series. Now see here n equals to n by n plus 1, and now we will also check the same condition of the alternating series. That means at first we should determine the limiting value of n, and if we see that n tends to infinity n by n plus 4, it is 1 by 1 plus 4 by n, so it would be 1 by n plus 4 by infinity, that is 1. So this is not equals to 0. So this series is divergent because the first condition is dissatisfied. Now go to the third example, where we should check the convergence of a series using the alternating series test. Given that n equals to ln n by n, now n tends to infinity, n equals to limit n tends to infinity ln n by n, And now see that if I substitute infinity in both numerator and denominator, I will get infinity by infinity, so that is indeterminate form. That is why we have to use L'Hopital's rule. We should differentiate both numerator and denominator with respect to n individually, and I will get 1 by n only, and that is 0. So the first condition is satisfied. Now we will check the second condition, that is whether the series is decreasing or not. In the above example, it was so easy to check the decreasing or increasing nature of a series, but for the third example it is not so easy. So we have to apply the concept of increasing and decreasing property from differentiation. So consider f of n equals to n equals to ln n by n. So f prime n equals to this function, and this would be obtained. Now for the critical point, here f prime n, that means this differentiation using u by v method. Now for the critical point, f prime n should be considered equals to 0, because at the critical point the slope of the tangent is 0. That means first derivative would be equals to 0. So after simplifying, I will get n equals to e. E has a value that is 2.718. That means now, since this is a single value, so we have to consider two intervals before and after the critical point. So suppose before the critical point this is 1, and after the critical point this is 3. Now if I substitute f prime on, if I substitute 1 in this function, I will get the result 1, so which is greater than 0. And if I substitute 3, I will get less than 0. Now go to the question. It was the series has started from n equals to 2 and end at infinity. So for a before the critical point, for a small numbers the series is increasing, but after the critical point, for a large number up to infinity, it is decreasing. So ultimately the series is gradually decreasing, so we can decide that the given series is convergent. Now the same thing we will apply here. Let's see, check the convergence of the following series. Given that n equals to root over n by n plus 4, now limit n tends to n, and after simplifying we will get 0. So the first condition is satisfied. Now in this series also we cannot easily check whether the series is increasing or decreasing, so we have to apply the increasing and decreasing property from differential calculus. So consider f of n equals to n and differentiate both sides, and we will get this result. Now for the critical point, if first derivative is equals to 0, so after simplifying n equals to would be 4. Now we'll take two interval before and after the critical point. So you can consider 3, that is less than 4, and another number 5, that is greater than 4. I have considered 3 and 5, but you can consider any number. It may be 3.5, 2.5, it may be 4.5 or 6, anything you can consider it. And we can say that if I substitute 3 at this differentiation, I will get this number, that is greater than 0. And if I substitute 5, I will get a negative number. So we can see that the series is f of n is increasing for a small numbers. that is open interval 0 up to 4, but it is decreasing for a large numbers, that is open interval 4 up to infinity. So ultimately we can decide that an is gradually decreasing. So both two conditions are satisfied, that is limiting value of an is greater is equals to 0 and an is decreasing. So the given series is convergent.